Okay, good morning, everyone. Hopefully, you don't get too sleepy back there in the back. But we will finish up chapter 15 today. We will go with a little bit of chapter 16. I think you guys have recitation today, so it's a busy day. And then you go on to your spring break destinations of home or other exciting places. Okay, so let's go ahead and pick it up right here with where we left off on page maybe 4 or 5 of the notes. So anyway, you're going to have these different situations here where keywords would be like more than, at least. I guess you could say at least is a keyword, and increase, if you will. And the alternative should be mu greater than, we'll say strictly greater than some value mu not. Okay, so it should be strictly greater than for that one, not greater than or equal to. Threw me off a couple days ago. So to just kind of strike the little at least, or the make the inequality strict, not a greater or equal to kind of a situation. Okay, so those are some keys there. And then you want to find the probability of a z being arbitrarily large. So as you might have suspected, we will look at arbitrarily large values of z from our test statistic, and I'll call it z test statistic, if you will, as a subscript. That's fine. And so anything out in this region here would give us reason to support the alternative hypothesis. So a keyword is more than. I like more than an increase more than anything else.
More than and increase, they're both greater than, right? And
yes.
At least is equal to or greater than.
Right. So just be aware of those kind of situations there. Let's see here. So then flip the script, if you will. So we're talking about more than and greater than. But on the other hand, you have these other guys. Less than, and then at most, we'll kind of put that in quotes. I'm not really keen on that one. And then reduced. So then again, the null should be mu less than some mu not. I think you guys have mu less or equal to. Just go ahead and scratch that, the equal to sign from the notes there. And so you want arbitrarily smaller values of z. And this time, the rejection region will be down there. We'll say z sub c for some critical value. So you have some cutoff point. You know, hey, you're no longer my friend, up to some cutoff point here. Go back. We'll call this guy z sub critical, sorry. Z sub c. And we'll do the example over here. So you have some cutoff point and say, hey, if the data value that you get is so large or so small, in this case, then anything smaller than that, I'm going to cut you off. We're going to reject the null hypothesis. So the question becomes, is our test statistic arbitrarily small enough or below our cutoff value? So h naught mu less than mu naught, and then some arbitrarily small values of z is how you do the p-value. So keywords are less than, reduced, those kind of things. shorter. You get the idea. Now this one is right on the money. So if we have a two-sided test, you're going to see words like different and is not, like a phrase there. The alternative could be two sides, either arbitrarily high or low. Okay? And then this way, because you have a two-sided situation, you have z critical values plus and minus, and the question becomes, where is my z test statistic relative to my cutoff points, if you will. Okay, so again, the classic example is everyone has some kind of internal barometer. When someone lies to you 4 times, is that strong enough evidence to defriend them? 40 times? Okay, yeah. Probably way out in the rejection region. So the test statistic is going to see where our data summarizes and falls relative to our cutoff points. And we have an example here. Now mu naught is the hypothesized value for the mean. So in our case, mu naught would be, I think we thought that students had like 8 drinks on average. Or we even said, I think it was 7. So whatever it is that you put down as a hypothesized value from your null hypothesis, that becomes our mu naught. We are finally ready for a big time example. So here we go. Suppose a random sample of 178 students yielded an average of 5.31 drinks per session. So we'll just kind of jot that down here. X bar is 5.31. And we'll assume a standard deviation of 2.98. Is this evidence that the average amount of drinks is different from our original estimate? Okay, so there are many steps involved. Please hang in there with me as we try to go through all of them. And to help you out with this, I put this on a... Okay, so there should have been a 4-step process that came with your notes when we started from last week. I sent it out. So we'll try to follow that 4-step process as much as possible. So the first thing we want to do is a couple things. Get my ducks in a row. With the so-called plan. Okay. And let's see here. What we want to do is see if the mu is the average number of drinks consumed for college students. So that's kind of like getting things all set up. And we will start off with 4.5 as our hypothesized value mu naught. Okay, so we have options. You want to use 4.5 or 7? Casey, did you give us 8? That's not 8's too tall. Okay. All right, so let's see. Let's go back here. Okay, so there's 8 right there. 7 and 8. All right, Casey, we'll try your 8. I think we're going to reject the null hypothesis. What do you think?
Yeah, probably not sure.
It'd probably get rejected for 7 also. Who has 7? Someone has 7. You said 7, right? Okay. So let's just say that, let's go with mu not being 7. And you're like, why does the dude keep changing his mind? Well, let's go. If we reject it for 7, guess what? We'll reject it for 8, right? Okay. So here we go. Go with 7. So that's what we're trying to estimate here. And then we're going to say that suppose the average here is 7. The alternative, maybe it's not 7. And again, I'm big on not changing the rules in the middle of the game, as you kind of are aware. Let's see here. Some background information as far as our conditions are concerned. Well, you want to see if you have a random sample. You want to see, let's see here. Do you have a large enough population? And let's see here. The third condition. Do you have a large enough sample? And give yourself plenty of room because there's more writing beyond this slide. So random sample. There she is. Yes. Large population. Okay, we're talking about college students. So I'm going to say that's a yes. The population of college students is arbitrarily large. And the sample issue, well, 178 is a lot bigger than 40, so I think that's large enough for sure. So those are some criteria for now and getting started. And yes, you will use this character today. In fact, this becomes your newfound friend for the rest of the semester, if it hasn't been your friend so far. Okay, so then what I chose to do, we changed to 7. Change to 7. My own guess was 4.5. I did this myself, but to use the audience data, we'll go with 7. So conditions, random sample, yes. Okay, so small enough sample or a large population. Okay, so the population of all college students is larger than 20 times the sample size. That's fine. That's pretty clear. Okay. And so we are not told the number of drinks per session follows a normal distribution. However, 178 is a lot bigger than 40. So we can use T, procedure, we would say Z, via the central limit theorem. Okay, so those are some conditions kind of helping us get set up here. All in the so-called planning phase. Now on to the nitty-gritty. All right? So you've seen this formula before back in chapter 11. And it's kind of reappeared here. So the sample mean was what, 5.31, and our hypothesized value was 7, right? So the question is, how far is 5.31 from 7 relative to standard deviation for the sample mean? Well, then you want to go ahead and do 2.98, which is not so bad, but then divided by the square root of 178. And I'm guessing it's going to be a big negative something. Negative 7.6. Woo! When was the last time you had a z-score of negative 7.57? Okay, so remember that whole issue, you know, do we have enough data to reject a claim or not based upon a z-score? Well, you have a z-score of negative 7.57. My guess, if you had some cutoff point here and some cutoff point here, we're probably clear down there somewhere, way in the negatives. All right. So let's just kind of play this out some. Let's find the probability of getting a z-score this small or smaller, if you will. Okay. And because we have a so-called two-sided test, we have to consider arbitrarily small values of z and arbitrarily large values of z. So to find the p-value, well, the probability of getting a z-score smaller than negative 7.57 is probably 0, right? Okay, so, but here's how you handle this. If you have a z-score that's arbitrarily small, let's just, for sake of argument, assume that the chart gives us 0.0001. Okay, it's off the chart, but we'll just assume 0.0001. You can assume 0 in this case also if you want to. So the p-value for a two-sided test means you have to double this probability for arbitrarily small values this way and arbitrarily in the mirror image 0.0002. So here's what we're saying. If in fact the true number of drinks per person was 7, then there's a 2 in 10,000 chance at the most of getting sample data as extreme as this or more extreme. So either my data is way off or my claim is off. Okay? So that's kind of what we're looking at here. Okay, so I did the p-value. And then let's see here. There is enough evidence to conclude that the average number of drinks is different from our guess of, that was my guess, 4.5, our guess of 7. Right? And a common alpha level or tolerance is 0.05. So that's a common one, I guess you could say. So the p-value of 0.0002 is less than alpha of 0.05, which means you reject the null hypothesis. So what probability are we willing to tolerate? 5%. Anything more than 5%, it happens due to chance error. The chance of this happening is 0.0002. Are we ready for the calculator? Okay. Yes, we're ready for the calculator. So the key steps here are going to be your conclusion, your p-value, test statistic, and getting things set up. Those are the key steps. So reject the H0, yes, we have enough evidence. And I'm going to say, Casey, that if we rejected the claim of the average being 7, guess what? It's probably not 8 either. Okay. All right. But I mean, you know, it's a good guess. I think it's cool. Now, here's the fun part. Please take out your calculators. You will thank me later with this. Let's go ahead and perform the test again. This time with the calculator. So, turn the calculator on. Go to Stat. Grapevine over to Tests, and the very first thing you see is called Z-test. Now again, if you don't have it, no problem, just look on with somebody else. And you guys are used to going down to Z interval, not this time. Just go to the first one. Stats, okay? And then this time put in all the given information. So I'll put in 7. I'll put in sigma of, what was that, 2.98. I'll put in my sample mean of 5.31. A sample size of 178. And then do we do not equal to, less than, or greater than? Not equal in this case, yep. And then calculate. As my kids say, bam, what? Alright, so negative 5.66. Negative 7.566, excuse me. I have, this is what, I'm just going to write this down, right? I have on my screen z-test mu not equal 7. I have z equal negative 7.566. I have a p-value that I'll come back to, a sample mean of 531, and a sample size of 178. You guys all know scientific notation, right? So I have 0.14 zeros and then 39. So I estimate the p-value is 0.0002 at the most. The calculator is even more precise. Basically, it's impossible. So the calculator is saying, hey, it's impossible for the true mean to be 7 if the data behaves this way. So either the data is off or the mean is off. This could be one of those times where I kind of ask you to raise your hand and give me a response with the clicker thing, but we'll do it old school. How many of you were able to get this screen on your calculator? Right? Okay, so life is good, right? Okay, so this is perfectly legal on a test or a homework problem or on a quiz, that sort of thing. Because we have time, let's for kicks go ahead and do a z-test for the claim that mu equals 8, just for case. Okay? Well, everything stays the same. Go back to stat, test, z-test. I'm going to change the first thing from 7 to 8. Everything else stays the same. So you should expect a z-score that's further from 0. You should expect a p-value that's even smaller. Whoa, negative 12. X bar and n are the same, and the p-value, I'm done here. We'll just call that 0, right? Okay, when you have times 10 to the minus 33, that's basically 0. Okay, so there you go. What's the process, if you will? You have a handout there, I think embedded within the notes, that covers the so-called 4-step process. Okay, so you want to state your situation. You know, what are you trying to test? You want to develop a plan for it, if you will. You want to solve it and make a conclusion. So those are the big 4. State, plan, solve, conclude. They're back again in this chapter. Let me take a peek at yours. Alright, so I know I hate to be pedantic, right? So state, plan, alright. Just making sure. Pedantic is like a academic way of saying nag, right? I hate to nag you about the whole thing. So then what's going on here? Well, what are you trying to test? That's the first thing we want to find out. Okay, you want to go ahead and state it a couple different ways. Then you want to kind of go through with your plan. So that's the state issue, the plan issue. Give me all the background information you have. Give me the null alternative. Okay. And then solve. What kind of conditions are working out for us? Come on. No. Danger. No, I don't want this. All right. There we go. We're good. Alright, so state plan solve, the test statistic, the p-value. So that's the state guy, the plan guy, the solve guy. And then the conclusion is pretty much, do we have enough evidence to say yes, you're guilty, or no, you're not guilty? And then we'll pretty much have this statement, there is enough evidence, blah, 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 blah. And the level of significance is the tolerance we're willing to take for the probability of the data being as extreme or more extreme than what we got. Alright, so I'm going to turn you loose slowly, right? Slowly. This should be Greek letter alpha. And we're going to end, I think, yes we are, we're going to end with this example. Kind of like how you see your homework and your quiz next week after spring break. So that's the background. And you think that people who drive nice cars and have other folks do their lawn work have high IQs. Okay, so you collect some data, and there's your results. And then the question is there a significant difference, or is your claim significant at this level? So what I tried to do was give you a page of the template. Don't write on that page. And then the next page is like a page to kind of fill in the various steps here. So let's roll with it. So the first question is, do affluent communities have IQ scores that are above average? That's kind of what we're looking to prove, if you will. And then this is just me being explicit. This is optional, I guess you could say. Or redundant, if you will. So that's the question. Do affluent communities have IQ scores that are above average? Yes or no, right? And so I'm basically saying here that mu is bigger than 100, if you will. But this is the key part up here. This is key. Next one. Okay, so identify the parameter. Well, mu is the average IQ score for all persons in affluent communities. And then what's given to us, the sample size is given to us, the sample mean is given to us, and I think we had a standard deviation of 15 that was given to us. And this is just kind of an ordered way of going through these exercises, so you don't forget anything, if you will. State the null and alternative. Okay, so in this class, for the most part, everything for the null will be equal to. The alternative is greater than. Now, why would it be greater than? What was our claim about affluent persons? Their average score was above average. or back here, yeah, they're above 100. So again, words like more than, above, greater than. Above 100 is the key there. The level of significance is 0.05. That was given to us. And in general, you have greater than for arbitrarily large values, less than for small values, if you will, below the mean, and then two-tailed. So then this will be a right-tailed situation because we're doing with large values of values larger than h naught and the mu naught. Okay, this one's a little bit trickier for you guys and not as required. But let's figure it out. So we have a right tail test, okay? And the area in the rejection region, as we call it, is 5%. So again, this is just kind of edification, if you will. It works out, my friends, if the area here is 5%, then there's a z-score such that it has 95% below that number. So if I do 5% to the right, that means that 95 is to the left. And if I do inverse norm of 0.95, I should get 1.645. Your textbook just focuses on this part. Right hand tail, a right tail test with arbitrarily large values of z, okay? But I just went a step further to be picky, if you will. And then this is called the rejection region. This is called a critical value. So z sub c is 1.645. You will only be required to sketch the curve and shade the right-hand side without labeling z sub c. What I'm saying here is that any z-score bigger than 1.645 is enough evidence to reject the null hypothesis. So let's go ahead and investigate. Okay, so check the conditions for the test you plan to use. Was it a random sample? Aye, sir. Okay. However you spell communities. All right. Was it small enough relative to the population? Yes. And large enough for normality? Yes. And then the test statistic is just plug it into the equation. So x bar minus mu naught sigma radical n 4.73. That's pretty darn large, 4.73 for our purposes. We're talking about 4 z-scores, 4 standard errors from the mean. And so the chance of having a z-score bigger than 4.73 is basically 0 or close to 0. Now before I go on to the next slide, let's use our calculators to kind of confirm all this. So go back to the calculator. So I go stat, then tests, then z-test. What do we put in for mu naught? Oh, 100, thank you. What do we put in for sigma? 15, I think. Sample mean of 112. 35 people. Do we do not equal to, less than, or greater than? greater than, and then calculate. Okay, so again, if you're doing this on your calculator, you do not need to show me this formula here. What you need to do is just write down, let's put it in a different color. Z-test equals to 4.73. And then the p-value, you'll put p-value anything with more than 4 zeros behind the decimal, we'll just call that 0. Okay? So I'm showing a p-value of 0.50 and then 11. And again, anything with 4 zeros in front, we'll just call that 0. So again, we're saying, based upon our data, yes, sir.
How are we going to put stuff like that into Stats Portal? Is it going to be like multiple choice? Or are we going to be like put 0, but it's going to count wrong? Just put 0.
We will make sure that you will not be penalized. If you are penalized, email your TA. Yes to that question or a stretch? You good? All right, good. Okay. So yes, we'll make sure that there's very tolerable. Last piece, conclusion. All right. So because our p-value and alpha, the p-value was basically 0. Alpha was 0.05, I believe. Yeah, 0.05. And back in your notes, it says if the probability of the event happening is very small, then you reject the null hypothesis. And then, so part A, we reject the null hypothesis. Part B, go back and answer the question. Yes, there is enough evidence at the alpha equals 0.05 level to conclude that persons from affluent communities have above average IQ scores or have IQ scores above 100. I guess it can go either way, but we'll tie it back to our original goal. Okay, there's a few notes there about the your homework and so forth, and we're not done yet. We have to do chapter 16 a little bit. So in your homework, you may have to do stat tests and then data. Right? It may give you raw data that you type into the calculator. So type that in first under L1 and then go back and do your analysis with the data component. Okay, I will post these over the weekend, and then we're not done obviously, but we will do chapter 16 here. Okay, so let's just see how this goes. All right. So okay, so here's some kind of attendance code 0409. you're supposed to text this number and put in that code. Let's see what happens. 1% of people are here. Good. Looks like more than 1% in my opinion. 2%. Okay, so I'm a novice at this stuff. So we'll just keep on trying. Okay, so you guys are here, right? So that's good. 6%. Okay. And I know some of you get your issues like, hey, you know, $20 is pretty steep, and it is. Or just you know, my cell phone doesn't work and that sort of thing. That's fine. Just let me know about those issues, and I'll kind of keep a little tab on the right hand side here. Okay, so you're going to text this 315 area code number, and then that's the attendance code 409, if you will. Can I put this in the side somewhere? Okay, so it's figuring it out. So 409, how are we doing? And I'm ready for chapter 16. Okay, we're in the 20s, so that's good. Put this on the side. There, that gets the job done. Well, all right. Let's go to chapter 16. I'll do the split screen thing for a little while. Okay, so you can kind of read through all that. What's the key thing with chapter 14? Well, that's confidence intervals. Chapter 15, test of significance. Chapter 16 is kind of like the idiosyncrasies, the nuts and bolts of both procedures. 409, there it is. Bye-bye. Okay. So then now we're going to do chapter 16, a few of the conditions. Do we have a random sample? Is it representative of the population? Was it from a randomized experiment? That sort of thing. You'll see me vacillate between large enough population and, let's see here, was the sample small enough? Okay, and then for things to work out from the independent standpoint, we need to have an arbitrarily large population. So is it 20 times as large as a sample? And then, of course, do we have a large enough sample? Can we assume normality? And you guys know that from the central limit theorem, the sample had to be bigger than 40, I think it was. So those are the three big conditions for inference. There's that. Okay. Random sample, larger population, larger sample. Confidence intervals. Watch out for the margins of error. Okay, for the sampling errors. Watch out for these big three. Under coverage, non-response. That was covered in chapter 8, I believe. And then, of course, the source of the data. Was it a random sample? Was it not a random sample? That sort of thing. Moving and grooving into chapter 2, or page 2, excuse me. What are some cautions about significance tests? And that was chapter 15. This guy is chapter 14. Okay. When the null hypothesis represents an assumption that's widely believed, use a small p-value. And here's the big kicker. The stronger the evidence for rejecting the null hypothesis requires small p-values, right? So again, you're close to 0. The further you are from 0, the smaller the probability is of being out in the tail. Small probabilities correspond to small p-values. And again, p-values that are below 10% can lead to rejecting the null hypothesis. And so that's where we did this a long time ago, which was like a couple days ago. Call this guy unlikely values, or extremely unlikely. Then we call this one unlikely. So then we have this guy as a red. This guy was an orange. I guess this guy was a blue or green or something. So we're saying here, for the most part, anything between 5% to 10% is in the unlikely category. And then anything less than 5%, we'll call that extremely unlikely. And you kind of see the connection. 90% confidence, 95% confidence, 99% confidence. Oh my goodness, that corresponds to more or less 10% levels of significance, 5% and 1%. So they are not distinct from each other. Okay, here's a little tidbit, if you will. Very large samples can yield small p-values that lead to rejecting the null hypothesis. And we have this issue between statistical significance and practical significance. Woo! Look at all that. So let's try to distill between these two concepts. So airlines. How many of you plan on flying during spring break next week? Wow. Where are you going?
Home.
Where's home?
New Jersey.
Okay. All right. Cool. Snooki is going to be there or no?
They're not from New Jersey. They're from Staten Island.
Oh, I'm sorry.
Yeah, we don't like them.
You don't like them.
No, nobody in the state likes them.
Neither,
We're all glad they're gone.
you're glad they're gone off the air. Jay Wow, all those guys. What's the guy with the Mike? Right? Gets in fights all the time. All right. Anyway, I do not watch MTV. Let's see here. Airlines are now monitoring the amount of carry-on luggage, or VH1, or wherever they are. Let's see here. So the average is 30. The standard deviation is 7.5. You sample 500,000 people. Holy cow. Was that big enough or what? 500,000 people, the sample average is 29.9. The test statistic is negative 9.43 with a p-value of 0. Okay, this is more of a comment, if you will, right? Practically 30 pounds and 29.9 pounds, about the same. If you're flying to New Jersey and it weighs 30 pounds or 29.9, about the same, right? Not a big deal. In fact, you get penalized for numbers of bags, not so much the weights. Well, I guess weight can come into it as well. But here, what's that?
I think it's dimensions.
Oh, if it doesn't
Weight
fit into the
doesn't matter,
box?
It has to be like certain,
Right.
so long by so wide by so deep.
It has to fit in some kind of compartment, right?
Usually overhead.
Oh, that's true. But then they have you kind of like stuff it in here. So anyway, what you guys could do on your calculator is verify this under Z-test, right? So Z-test, you plug in all this information, you'll get the Z of negative 9.43. You get a p-value of approximately 0. And if you did it by hand, it would be this: 29.9 minus 30 over 7.5 divide radical 500,000. Negative 9.43. So all I'm saying here is that from a practical standpoint, maybe you do have statistical significance with some small p-value, but practically 29.9 and 30, pretty darn close from our standpoint. So having a sample size that's too big can almost be detrimental to you, right? It leads to rejecting the null hypothesis when you don't need to. Moving and grooving. Last concept. Okay, we talked about this before, the sample size for confidence intervals. The margin of error is this guy. So we saw this in chapter 14. So now we're going to refer to it as M, the margin of error. And because you're so well versed in your algebra skills, if I take Z times the standard deviation over the square root of N equals the margin of error, you know how to solve for N. Yes, yes you do. Well, you want to square both sides. Then you get Z sigma squared and squared over N equals M squared. So then you get N equals Z squared sigma squared over M squared. So that's pretty much this new formula for chapter 16 is just a previous formula rewritten, and you get this guy. Alright, so we'll knock this out really on Tuesday. Well, which is like 2 Tuesdays from now. So we'll pick it up right here on Tuesday the 20th or 18th or 19th.